Methods for h2o frames. Well, firstly, let's create a matrix. So we've got a matrix which is what? It's a NumPy array, which it should be. What I'm curious is what is the shape of this thing? Okay, that should have been fairly obvious. It's 100 rows and 4 columns. Let's have a look at some of that data. Well, it's not very exciting. Let's store it as a pandas data frame. There we go. How are we going to send this data to the JVM? Well, I think we should be able to know that now. It's going to be something like, again, we've just called it the same, haven't we? dfall and destination frame equals dfall. Now, this is, as we've said, it's a handle to that data, that h2o data frame, which is living in your JVM. But we've been given methods for it. We're told we can use head. You might be surprised to see 10 rows here. If you remember, if you're using pandas, the default is 5. Well, not a problem. Tail is exactly the same, unsurprisingly. Columns, you can find all the columns in your data frame. We can do columns to our h2o frame. And once again, it's sending an HTML message to your Java virtual machine. It's finding out the names of the columns and then it's sending a message back here to tell you what they are. Or we can do types. In pandas it would have been D types. They're all reals. In dfall you can do describe. In pandas you can do describe. You get things like the mean, the standard deviation. What do we get? Well, you get stuff, basically. It can't say it's quite the same. You can decide for yourselves which one are more useful. Which one is more useful. Now, how do you select columns in a h2o data frame? Well, you can simply use an integer and you'll get, that will give you the first column, the second one, and so forth. Or you can type it by, you can actually type the column name in directly. In pandas, you've got to be a bit more explicit. Do you think you can do this in pandas? No, you can't. If you wanted to try and get the column in pandas, you've got to do something like dfall.iloc, which is the integer location, I think that stands for. And then you say you want all of the rows and just the first column, and then you will indeed get it. So it's a bit different. It's not all the same. Slicing, if you want 2 columns, you shouldn't be so surprised that that would give you 2 columns. Well, if you did it right, it might. Right. Summing rows and columns. In pandas, use the .sum. You tell it which axis you want to squash. So here you're summing down axis 0, so you're squashing it, so you're just left with the columns, or you can squash the columns and you just end up with the rows, the sum of the rows. Or you can use dfall apply, same kind of thing. So instead of .sum, you can apply a function. It could have been the mean if I wanted. Well, that could have been if I had done it properly. Or the min, any function can go there. Now, I'm not sure if you've come across lambdas, anonymous functions. If you haven't, I'm not going to explain them here, but please do look them up, they'll be useful for you. But what is this function doing? Exactly the same as we did before, but we've now created a function to sum x. Why did I bother showing that to you? It's because I think that if you do this in h2o, you do need to do it with the apply method. So if we want to find the sum of each of the columns by squashing the rows together, summing them up, we can do it like that. Fortunately, 6.463432, 6.46343, it's the same. We can choose a different anonymous function, and so on. Right, missings. Well, we've kind of talked about missings. I'm not sure I'm going to say very much about them, but let's just see how h2o handles them. what would we expect if I'm looking at this? Well, there's an NP-nan there, which is pretty much how pandas likes to handle it. That's a float, so we'll have to upcast all of those to float. Non is an object, but it won't even store non as non, it will store it as NP-nan, and then again it will upclass column B to a float. That NA over there does not look very exciting, it just looks like the string which has got a capital N and a capital A in it, so that's not really missing at all. But this one is missing. It's a non, and I don't know, I think it should be fine storing that as a non, but we'll see what happens. So in pandas, it did store that as a non-object. It was quite happy with that. That NA over there is simply a string with the contents capital N, capital A, and those two have been stored as np.nans. You can see, like I said, that one is just the string NA. The first two have been upcast to float 64s, the second two are objects, which is what they would be in any case. Now, let's create the same data in h2o. We're telling it the first two columns are numeric. The third one is enumerated. We're going to see what that means in a little bit, and the last one is a string. The first two have been upcast to nan. The third one is stored as the string NA, which why shouldn't it? But the fourth one, which was a non, is not being stored as the non-object. It's being stored as an empty string, which is, to my mind, a little bit different. Now, the method is.na will find missings. I wonder what it's going to find for this one over here, the one which is just changed into a string, empty string. These two here clearly it's going to find. That one it will not find because you've just stored it as a string with an N and an A in it. And that last one, let's find out. No, you can see although we put non into it, it changed it to an empty string, but an empty string isn't missing. If we take operations on columns, the default is to exclude missings. You can see that because otherwise it would have been missing. na.rm equals true would have been the same, ni.rm equals false would have been nan because it can't add missings together. There's lots of other methods, we're not going to talk about them, they're in the booklet and I hope you're going to read the booklet, but let's just talk about the enumerated data type. This is the same as a factor in R, so anybody that is familiar with R will immediately know what I'm talking about. But let's just have a look at it otherwise. So we have a data frame, which is not very exciting, foobar, and so on, and stuff in the second column. But the types, although I haven't told it to, interestingly enough, it's stored the types here is the enumerated types. Now, what's really happening is maybe easiest if we just look at the levels of these enumerated types. It's realized there's only two levels for foo and bar. It's called them, well, it's probably called them levels 1 and 2, or level 0 and 1. And level 0 is bar and level 1 is foo. What will be happening internally, it won't be storing all of those strings individually, which could take quite a lot of memory if they're long strings. It's just going to store 0, 1, 0, 1, 0, 1, and once off it's going to store the levels, which tells it that level 0 is bar and level 1 is foo. We will talk later about interactions, I hope, so long as we have time, but it's good to know that you can actually create interactions. It is basically just concatenating these two variables together to give a third variable, which has possibilities of all the combinations of the first two variables. If you are creating interactions for the purposes of analysis, sometimes you want to limit the maximum number of factors you can have. This one clearly only occurs once, and so it's been set to other. That's really it. This is probably one of those kind of things which I just think you're going to have to work through the booklet at your own pace. I've tried to talk through some of these things, but just go through the booklet.